All right, so we're going to be moving on to actually doing antiderivatives. I'm very excited. So a match made in heaven. So far we've been using integrals to represent accumulation of change, an area under a curve. And then in yesterday's videos, we explored the idea of the fundamental theorem of calculus and how to evaluate them by hand. In order to do that, we need to know some rules about how to do the antiderivatives themselves. So we're going to look at some key features using graphs and then see if that can help us get to equations. So two polynomial functions are shown in this picture, which was the original and which was the derivative. So we've got colors, and you don't have color on your paper, but we've got a red graph that is going from here and then going up to 4, and at 4 it turns around and it has a minimum at 2, and then it turns back around. And so what we want to do is make sure we're using calculus reasoning and not just which one's original and which one's the derivative. So take a minute, pause, come up with your own ideas, write them down, and then we'll talk together for a second. Okay, so I'm back, and so when we look at this, clearly the red one, which is a cubic function, is the original, and the blue one, which is a parabola, and a squared function is the derivative. And we can say because, well, one's cubic and one's squared, but we got to be a little bit more clear than that. So even though that's a good reason, it's not a great reason. And so, yes, our cubic function is the original. And our parabola is the derivative. But we don't want to just go every cubic function and parabola related. These two are related for more than just because one's cubic and one's parabola. So what we notice is right here at 4 on our cubic function, the tangent line has a slope of 0. And notice on our derivative that the value is 0. We also notice here that we have a slope of 0 on our tangent line, and then the value of the derivative is also 0 at 2. So that's important that they're the zeros match. And the other thing that's important, the reason I know this blue curve is actually the derivative of the red curve, is because this is a maximum of the red. We can see that clearly. And when we look at our derivative, it's positive and then negative, and we know that when it's positive slope to negative slope, that's a max. And we can see over here that the slope is negative and then the slope is positive, which is a minimum, and that's what's happening here. So we can look at the derivative in that way and grab some of that information. And what I really like here, I'm going to go ahead and jump to the way Calcmatic themselves explained it. So you got the original and derivative marked here on the picture. Parabola's derivative of the cubic is the original. When f, the original, has a max or min, f prime has an x-intercept. When f is increasing, f prime is positive, and when f is decreasing, this is the vice versa. When f is decreasing, f prime is negative. And I think that's really important, those kinds of ideas, because there's a lot going on here, and we need to make sure that it's matching everywhere, not just some places and all the places around. So you should have, along with this piece of paper, a bunch of graphs to use. And one side at the bottom of the page, it says original functions, and the other side at the bottom of the page, it says antiderivatives. And so those are the ones we're looking at and for the rest of this lesson. So it talks about orange and yellow, and since I wasn't there, I didn't copy things on orange and yellow. So orange is the original, so that would be the I believe blue side. Let's look again. The original is the ones that are blue, which you can't tell, but your second page, and then the red ones are derivatives, or antiderivatives. So in other words, we're saying, hey, if I know this, the original function, and can I figure out the antiderivative? Can I undo it? And so what we see in these cards, and you're going to try to match, and I think it's pretty obvious in some cases what's going on because they're not mixed up and shuffled or any of those things. But like you can see here, this is a constant slope of 1/2. What would the antiderivative be? Well, it would be an equation with a slope of 1/2, which would be a line. And if you see like this one, that could clearly match that. A can also match that one. So what's going on? Which one matches which? And so that's important. So what I want you to do is go ahead and try to match them all up. You might want to number one side 1 through 12, and the other side A through whatever the 12th letter of the alphabet is, and then match them that way. Go ahead and do that. I want you to pay attention to how you know, and not because they're in the same place or something ridiculous, but how do you know which one matches which? How do you know that this is the derivative of that? So like here we have a sine wave, and here we have a cosine wave that's opposite of cosine. Are these two derivatives antiderivative of each other? What we know about cosine, when we take the derivative of cosine, we get negative sine. And so if we have negative cosine, we took the derivative, wouldn't that give me positive sine? And so just kind of keep those ideas in mind while you're matching. And I do think there's an order to these. Don't let that be your thing. But I want you to talk to each other. Go ahead and do all of the matching you can. I'm not going to do any of the matching for you. I'm going to give you a list of things, but I'm not going to do the matching for you. I want you to do that matching yourself. It's important to match things up and to know what's going on. But once you've done that, write the equations. We're going to call the original functions f of x, or f, which is capital F prime. And then we have f here. And so that idea of writing the equations, we've got 3 different equations that are just negative 1/2, one that is positive 4, one that's 1 over x. And so these are the original equations, and can you come up with the others? So go ahead and pause, do all your matching. Sorry, I should have said that earlier. And then we're going to make our chart. So this is the one side of the chart. And then I'd like you to try to figure out the other side of the chart. I do have all the answers. You can see some of them kind of peeking out. But see if you can, by looking at the functions, come up with the exact right answers, and then see why, if you undid the derivative, why you'd get that. So take a minute, do all that work. The next video will be discussing the back, so this will be the end of this one. In about 30 seconds, I'll put the answers up here. That's a lie. It'll be really fast. But pause, take the time, do it yourself. It won't help you if you know all the answers without doing the work. Do the work. Go through the trouble. Take the time. And again, with these ones that are all the same, it doesn't matter which way you wrote the equations and which ones you matched with which, because the derivatives would match, so it's okay. And here come the answers. So I hope you paused it. I hope you paused it. I hope you tried. Did you try? Did you try? Did you try? Okay, here's the answers. So I'm going to go ahead and put that up here. Go ahead and copy, check your work, see what's going on, and then in the next video we'll discuss some of the rules.